board is the continuation of the statement. Now, there are two cases depending on the sign of the overflow. If the overflow is negative, then generically means unless you are really unlucky, unless you're in an exceptional, strange situation, the K and L don't intersect. You can just fit them without any overlap. If, in contrast, the overflow is positive or zero, those of us who learned mathematics in the English-speaking world will call this positive or zero, because for us positive means strictly positive. Those of us who learned mathematics in the French-speaking civilization will call that just positive. And if there's no equality, we'll call that strictly positive. I'll combine these terms. So if the overflow is positive or zero, then generically the intersection is non-empty. In other words, there is an intersection, and the dimension of that non-empty intersection, if you like here, the point at which two lines meet, or the line along which two planes meet, and so on, is exactly equal to the overflow. Notice that this can happen, the second case can happen when the overflow is zero. That means that two submanifolds meet in a zero-dimensional intersection. But zero-dimensional intersection does not mean no intersection. It means meeting in points. Points have zero dimensions. Yeah, it does not mean, oh, that's interesting, something happened there. Okay. Now, this is, you might say, elementary linear algebra. And that's it for the proof. Well, this is the kind of thing that professors will often do. They say, oh, you have learned linear algebra, and you know everything about linear algebra, and the fact of the matter is we learned linear algebra a few years ago, and we don't quite remember what was linear algebra, and then they say, oh, it's elementary linear algebra, and then go. It's not kind. So I'd like to give you a picture in order to understand this, make it more intuitive. However, the picture that I shall draw is not a picture, but we shall call it a picture. Let's imagine that you want to put the k-dimensional space, subspace. How do you represent a k-dimensional subspace? Well, how many parameters do you need to represent a k-dimensional subspace? Well, k parameters, right? Let's say that you have an n dimension, the ambient dimension is n. So k-dimensional subspace looks like this. You have some parameters, k of them, which can take arbitrary values. Yeah? You go in k independent directions, but the remaining directions will all be zero. Does that make sense? Think of, for example, R3. Let's say that we want to have something one-dimensional inside the Euclidean space, R3. How do you do that? Well, you can represent it by this. X can be anything. This represents, when x takes all values, the x-axis. Y and z directions are constrained to be zero. Boom, boom. And that's one dimension. If you want a two-dimensional object in R3, you can do this. X and y are free parameters. They can take anything. So this, when you vary x and y, will move all over the horizontal plane, but the vertical coordinate is constrained to be zero. So that's two-dimensional. Okay? And that's exactly the same thing, but in higher dimensions. Okay, so that's the k-dimensional case. How about the l-dimensional case? Well, again, there are m components. And let's try to make the overlap as small as possible. That means that you see there are lots of non-zero numbers here and zero numbers here. So I want to put all the non-zero numbers at the bottom and make 0 at the top. So we shall put the L-dimensional submanifold and parameterize them by putting it in this form. So there are L entries which are completely free, so they can take arbitrary numbers, and the rest are 0. Okay? So that's a k-dimensional submanifold, that's an L-dimensional submanifold inside a common ambient space that has dimension n. Now, question, do they overlap? The answer is they overlap if and only if this comes down far and this comes up far. If there are not many of them, they don't overlap. Okay? But you see, what's the overlap? That's K and L and M. You can figure out the overlap. And because some of us are feeling the temperature, if you have general K, let's say that K is quite large and L is quite large, how much overlap do you get in the middle? No. You have K, the whole length is M, and you start filling K slots from above, L slots from below. And they sometimes overlap. What's the overlap in terms of K and L and M? Yeah, no. What's the overlap? Let's do it in 3D. 2 dimensions, x and y and 0, and then maybe y and z and 0. So this is also 2 and 2 inside 3. What's the overlap? You overlap in the middle, right? Overlap dimension is 1. That's because there are 2 here, but the ambient dimension is 3. You start overlapping. So what's the overlap dimension in the middle? Yeah, so, but in terms of K and L and M, how much overlap is there? K plus L minus M, exactly. And that, guess what, is the definition of the overlap. So that's the overlap dimension that you get. And this is, as I say, the picture of this theorem. Do you understand what the picture is? It's very strange. I didn't draw a picture, but in some sense, you can see that you are thinking geometrically when we do this. In terms of a simple example that you kind of visualize, you are not, of course, visualizing because K might be 200 and M might be 500, higher dimensional spaces, but we still feel that we understand. That's one way to do geometry. Okay. Any questions? And it's getting very hot, so, well, I thought in Madagascar it was hotter than this, but it's, of course, it's also after lunch. Next week, we'll be doing this before lunch when everyone's hungry and quite nervous, so it will go better. Okay. Now, so far, we had a static picture. In other words, submanifolds, manifolds, and so on, they were not moving. They just stayed there, and we contemplated them. We just watched them at rest. Let's start moving one submanifold inside a manifold and try to go around an obstacle, run into an obstacle, and so on. Let's move submanifolds. As before, we'll start with some illustrative examples, and then we'll be able to guess what the general result is. Again, in R2. Imagine that we have a line in R2 and a point on one side of the line. And this point, which you might think of as, say, Tadashi, and this is the river, wants to go from one side to the other side of the river. Well, at some point, Tadashi's feet will get wet. It's sometimes known as the intermediate value theorem. Okay? So, in R2, so 2-dimensional space, a point which has dimension 0, moving from one side of a line to the other side. And please don't worry too much about what we mean by side. One side to the other side of a line which has dimension 1 must make a crossing. Okay? The situation, you realize, is a little different from the static situation before, because you see, this is dimension 0, this is dimension 1, dimension is 2, there's a lot of ambient dimension, and nonetheless they must intersect. Why do they have to intersect? 0 plus 1 is less than 2. Overflow seems to be negative, and nonetheless they must intersect. Next, if you do the same thing in R3, a point moving from one side to the other side of a line, Tadashi starts going there, but then he sees that the river is coming. And he wants to avoid the intersecting the river. What does he do? Where is the stick there? Huh? Exactly. He comes like this, and he goes, whoop. I could jump because there was a third dimension into which to jump. I could escape into this extra dimension. Yeah. Hop. It can avoid the crossing. Okay, that's interesting. Let's think about this. In R3 then, a line which has dimension 1, moving from one side to the other side of the line, from one side to the other side of a line, another line, which also has dimension 1, what happens? In order to do this, would you kindly hold this like that, and then don't let it go? So that's one line. We are inside a three-dimensional space, and that's another line. And please imagine that this line goes up and down infinitely. When I come across, I have to make a crossing, right? I cannot avoid this crossing. I might try to go, but I might try to go. You might be thinking, what about this? But remember that this line is infinitely long, so it goes. So there is no way to avoid a crossing. However, in R4, four-dimensional space, it can avoid a crossing. Hey, can you hold it again? How do we avoid the crossing in R4? Well, this is the line, infinite line, and it comes. And then it's like Tadashi earlier. When it comes here, he wants to jump into an extra dimension. It jumps, and so this part disappears from 3D. Just as, excuse me, when I was jumping across the river, I disappeared from the two-dimensional plane. I left the two-dimensional plane, so if you are just observing me in the two-dimensional plane, it looks like I disappeared, and then suddenly appeared again. Yeah. Whoop. Woo. So it's the same thing. I deform myself into a higher dimension, and then reappear here. And I can cross over. It's perfectly rigorous. So in R4 it can avoid a crossing. Amazing stuff. So, what is the general theorem? And this is the main fact that underlies the operation of isotropy. The dynamic picture of crossing and not crossing. Theorem 2. So imagine that you have two submanifolds, KL, inside M. And they're such that the their overflow, which we define, I'd like to remind you what it was, dimension K plus dimension L minus dimension M, that's the overflow. Now, do you remember in the static case, overflow had to be strictly negative in order to avoid intersection. In other words, strictly less than 0. But here in the dynamic case, when you move one thing past each other, you see that you need a little more overflow. And so we'll start from 0 and less than 0 so that you do get some intersection. So that, so that you don't get the intersection initially. So that the theorem 1 by theorem 1, initially, they are not crossing. Now, suppose that I start moving. Then they might start crossing, you see. So K moves just like those examples. Bear in mind those examples, please. From one side to the other side of L. Starts moving in that like that. And we really want to avoid crossing. Tries to step aside or step around as we did when I jumped or as we disappeared into the next dimension and came back. Okay, step around to avoid the crossing. Okay. Theorem, or the result, if the overflow, we know that overflow is negative, but if overflow is sufficiently negative, that is less than or equal to minus 1, is equal to minus 1, then it fails. Excuse me. So, crossing is inevitable. Happens. Whereas, if the overflow is less than minus 1, then it succeeds. That is, crossing is avoided. That's the theorem. As usual, it's much better to draw a picture and understand it in terms of the picture. Indeed, writing it like this in words makes things look complicated. In fact, the way I prepared this statement is I first drew a picture and then looking at the picture, described it in words. That's the order in which I did it. I didn't have the statement and try to draw a picture. It's the other way around. So here's the picture. Remind me. Zedia. Okay. So let's draw Xavier and Tadashi. There are two people and they are having this submanifold L inside the manifold M, and then Tadashi is trying to do crossover. So this is K, and it's moving forward. Okay. And the question is it going to cross or not? Or can I avoid the intersection? Now, here is the idea. As K moves, we thought the dimension of that matter was dimension of K, but in fact it isn't. When K moves, imagine that K sweeps out the whole screen, whole surface. Okay? That's the trajectory of K. It's leaving behind sort of a cloud, smoke screen. And that has a lot of dimension, and the question is whether L is going to intersect that trajectory of K. So as K moves, it sweeps out. Do you know this expression? Yeah? Do you know this expression? So when I move, for example, something like this, can you imagine the surface that is left behind when I move? That's called the surface swept out by this stick. Okay. And if you have a point, it moves. What is swept out by this point is a curve. Okay, you sweep out, because sweeping is what you do when you have a broom and so forth. Okay, it sweeps out a surface of dimension. What's the dimension? Dimension K plus 1. Okay? So stepping around, as we call it, to avoid the intersection would be successful if there is enough ambient dimension to avoid the intersection between this screen, this swept out surface, and L. If this surface, or let's call it sheet, because that's probably more suggestive. If sheet, yeah, does not intersect L. But what is the condition for the avoiding intersection? By which theorem is this? Do I have it? Is that number 2? Yeah, that's right. By theorem number 2. No, theorem number 1, excuse me. Because we're using theorem number 2 is what we're proving. Number 1 is what we already know. Sheet and L will have empty intersection generically. You can sort of generically perturb it to eliminate intersection if the overflow, which is 1 plus dimension of K, that's the dimension of the sheet, yeah, plus dimension of L, minus dimension of M is negative, strictly negative. But what is this? It is simply equal to, this number is overflow, so it's 1 plus the overflow. And you see that, therefore, it's successful. You can avoid the crossing if and only if the overflow is strictly less than -1. That's the condition. If it's equal to -1, you're in the case where this sheet and L intersect in points in zero-dimensional things. That's the conclusion. Okay. I'll add 1 or 2 corollaries, and then that's it. Okay. Have you heard of knot theory? Huh? Have you? Knot theory. First of all, knot theory doesn't mean knot theory. It's knot theory, knot theory. So theory of knots. Things like that. This is knotted. This is not knotted, and so on. Knot theory, have you heard of this? This used to be quite popular, but maybe nowadays it's not so popular. So I'm going to show you that knot theory is a very special subject, and it's not generally applicable. First, corollary 3. You know, if you have something like that, without cutting, you cannot unknot it to make this. Yeah? I should have brought a string. In fact, somebody was doing this last night. Yeah? You cannot unknot this to make this. Yeah, you cannot, because if you have a string, imagine that this is made of string. I cannot make it into this shape inside R3. Do you agree? Yeah, you can see this? I really wish that I was wearing a shoe with shoelaces. Does anybody have a shoelace? No? Okay. Okay. Do you know what I'm talking about? Do you know what the shoelace is? It's the string that you have to. Monde, can you lend me your shoelace in a moment? Okay. Ah, you have a. Oh, that's. But I cannot cut it, right? Because we have no scissors somewhere, anywhere in Ames. Thank you very much. Thank you. I'll return it. And so thank you very much to Monde for his support in the mathematical sciences. Yeah. So this is a simple loop. But now let's take something else. If we have something like that, let me tie a knot. Excuse me. Yeah, something like this. Yeah. I cannot undo this knot. What am I doing here? Anyway, something like this. Yeah. I cannot undo this and make it just a straight. Yeah, it's clear, but I cannot undo this in 3D. But that's because I cannot undo this because we are in 3-dimensional space. In 4-dimensional space, we can. We can sort of go to the 4-dimensional space. It left, and it will come back in a moment. It's in the 4-dimensional space now. Just 1 second. It takes quite a while to go to the 4-dimensional space. Yeah, but that's because Egyptian women have special vision. And it comes out like this. So, that's the statement. It sounds crazy, but we shall see that it is true. So every knot made of strings, every string knot, excuse me, made of a curve, I'm going to discuss other things, so made of curve can be unknotted in Rm for all m from 4 dimensions and above. In 3D, you cannot. That's why we have all those knots in 3D in our space, but in higher dimensions, they can all be unknotted. And the proof is very easy. You see, suppose that you have 2 parts of this string. One part is like this, and then another part is like this. It's passing behind. And suppose that by some magic, I can make this part of the string come across and appear on the other side without intersecting. Well, if I can do that operation, I can unknot everything. Right? So the question is, can I do this operation or not? And we can in this dimension. This move is possible without crossing. If by the theorem that we have just proved, theorem 2, the overflow, which is 1 plus 1, because you have one dimension here, one dimension here, and minus the ambient dimension m, is strictly less than minus 1. But this inequality says that m is strictly greater than 3. That means m is greater than or equal to 4. Okay? So oops. In other words, in 4 dimensions and above, all knots can be unknotted. There are no knots. Everything is trivial. That's quite interesting. However, another interesting thing is in R2, if you go down too much in dimension from this space to plane, on the other hand, in R2, so we have R4 and above, but in R2, a loop like this might be a nice loop, but it could be a loop like this. It might cross itself. Now, may you borrow this? So if you have a loop which is crossing like this on the plane, well, your natural instinct is, what's this? I don't like this crossing. So I'm going to undo the crossing by lifting one strand of the loop from the other. Now they don't cross anymore. Yeah? But that undoing the crossing is possible because we have an extra dimension into which we can escape. In R2, you may not be able to escape. For example, this is stuck. However you move, however you put up, this crossing will survive. So in R2, a loop like this may have generic self-intersections. In other words, intersections that cannot be made to disappear by small perturbations. Yeah? And that's by theorem 1, if you do the calculation of the overflow. So it means that in R2, usually knots or loops have self-intersections, which we don't like. In R4 and above, all knots are trivial. So the only dimension in which knot theory is interesting is R3. There is no other dimension. Okay. Knot theory becomes completely trivial in R4 and above, and becomes too ugly in R2. The only dimension where knot theory is interesting is R3. So that's knot theory. It's a big subject, so you might like to look it up, but it's interesting only in R3, dimension 3. Okay, that's enough.